So you are welcome. So let me know if you are around so that we can all be on the same page. Okay, Ajalimo, you are welcome. Yes, Onulapo Abolaji, we have Yeroku Mavelos, Olaitan Shudebiri Anoze. Okay, you are welcome. So let us have more audience before we start. So our today's topic is sequence of real numbers. So if you have any issue, so just let me know in the comment section. I will attend to them. So we have Kamalidin Apaokaki, we have Samuel Adishola. So you are welcome. Ibrahim. So you are welcome. So I think it is more honorable for us to start now. Skid. Hello, Skid. Just say hi. I want to know if you are following. All right, thank you. So can we see this perfectly? I want somebody to answer before we start. Can you see the board perfectly? All right, thank you. So, sequence of real numbers. This is the second aspect of this course, and it is all about real number, like we have said. But the concept we are trying to look about as today is sequence on real numbers. So, literally, when we say sequence, what do we mean by sequence? Okay, without the word real numbers, what do we mean by sequence? Okay, sequence normally is a particular arrangement of objects, or this object will be numbers and what have you in a particular order. Okay, if I have several objects, or in this case numbers, okay, and I want to arrange this object or numbers in a particular order, okay, we use the notation just like we have in under the set theory. We use this notation, the curly bracket or brace. Okay, let's say these objects are A, B, C, D. Then we have them continue like that up to N. Okay, so this is sequence of lowercase numbers. Okay, as you can see, we can rearrange this. Okay, in such a way that it will suit what we want. But when we say sequence of real numbers, okay, this is the arrangement of numbers. Okay, these are numbers whose domain is a set of natural numbers. We'll come to that literally, but let me just explain that. If we say sequence of real numbers, okay, if the domain of that sequence, okay, is a natural number, and the output in the codomain is real numbers. Okay, so that's what we mean by sequence of real numbers. So let us go back to this. When we say sequence, in this course, we'll give each element of the sequence a position. Okay, a position number. Like if you have this first element here, okay, we want to use the notation xn, okay, where xn means x of n, okay, for this small n is the natural number, and when I make position is natural number start from 1, 2, 3, 4, okay, it's just for arrangement. Now, if n is 1, the first element in the sequence we take x1. So when n is 2, okay, it's like saying x of 1, x of 2, because it's the function as we'll define later. So when n is 2, the second element will take x2. Okay? So this b here is taking the position of the x2, for example. And then when n is 3, you have the third element of the sequence, and that's how it is. So in this course, we'll be making use of x1, x2, okay, to label the position of a particular term of the sequence. Okay? Now, let us now define what sequence of real numbers. So, how we know this? Okay, let us now define sequence of real numbers. So, how do we define this? Using some elementary mathematical annotations. Okay, if you have noted this, so I'll call this definition 2.1. Okay. So, like I said earlier, the sequence of, I said for any sequence, we're using x of 10. Okay. And such a sequence will be represented, okay, using the curly brackets. Okay. What this notation means is that when n is 1, n that we are choosing here is the natural number. Okay, so when n is 1, we can have x1. When n is 2, we have x2, s3, and dot, dot, dot. Since n goes to infinity, so we have dot, dot, dot. Now, I'm referring to the sequence now. We'll define the sequence, okay, as a sequence of real number. Okay, now, I'll say a sequence xn. Okay, if I say sequence xn, okay, we'll put the range of that sequence. That sequence ranges from 1 to infinity. Okay, just like we have it here. So a sequence xn is a function whose domain is a set of natural numbers and its codomain is this set of real numbers. Okay, so this is how we define sequence of real number. We have defined it as a function. You know, when we say a function must have a domain in mathematics and it must have a codomain. Okay, So notationally, what we mean by this is this. Intentionally, a sequence that we are referred to here is a function whose domain is natural number. Okay, and of course, we have said this n here is a set of natural number is what we refer to as the domain of this function xn, and the codomain is this. Okay, R. Now let us now see some examples of sequence. Okay. So the term xn equal to 1 over n. Okay. Now, for us to see some element of this sequence, we need to, expand further this way. Now, let us look at this. If n is 1, this will be, if n is 1, this will be 1 over 1, and this will be 1. When n is 2, this will be 1 over 2. When n is 3, this will be 1 over 3. And we are going to have this. This will continue to infinity. Okay? So this is how the sequence of so the term this is a sequence of real numbers. Okay, so we will observe that for each n we pick here, the output is always here. Okay, when n is 1 here, okay, we have 1, which is also a real number. So when n is 2, we pick 2 from here. Okay, we found that when this is 1 over 2, 1 over 2 is a real number. So when n is 3, that's 1 over 3, which is a real number. Okay, and so on and so forth. Okay, so since n goes to infinity, okay, since n goes to infinity, check if the video is not clear, check the resolution of your video. Okay, it means you need a very high resolution to watch it clearly. Thank you. So this time is a sequence of number as we have explained. So you will observe, if you want to relate this to what we know earlier, okay, you will notice that this interval, okay, though it's starting from 1, I mean this sequence is starting from 1, okay, and as it is going, eventually we will reach a number, then we stop. So later we'll talk about the convergence or boundedness of the sequence, okay. But just to also see that the entire number here is actually in this set, okay. If we are to write all of the number here, we see that, okay, as n goes to infinity, okay, the last number here is going to be 0. The last number, as n goes to infinity, the last number is going to be 0. Okay? And because of this, since this is the entire number we can have for the sequence, it means if you want to arrange this in a given interval, this is 0 to 2. Okay? You know, when we are coming to the interval now, okay, of a subset of R, we have to arrange the number orderly. Okay? Orderly means 0 come before 1 and 1 come before, sorry, 0 come before 1. Yes. So the entire number in this the entire number in this sequence is 0 and 1. Okay, so you now observe that this interval is a subset of R. Okay, so as it is, we can relate this interval or use this interval as an example of the first part of this course. For example, if you want to know the infimum of this interval, okay, already we know the infimum will be 0, the supremum also will be 0, and you can also consider other things there. Okay, so where we are going is the entire sequence there is embedded in R. That's where we are going. Okay, so let's take this as example 1. Now let's see example 2. So if you have any question on this, let me know. If there is none, so let me know. Let me know now. Is it clear now? Samuel, let me know if it's clear now so that we can continue. All right, thank you. So example 2. So the term xn equal to 2n over n plus 1, where n starts from 1 to infinity. Again, this time, we want to see whether it's a sequence of real number. Again, if you take n to the 1, okay, this will be 2 multiplied by 1, then 1 plus 1, that is 2 over 2. That is 1. The first element there is 1. Okay, so when n is 2, 2, 2, that will be 4. 2, 1, that is 3. Okay, the next number is 4 over 3. When n is 3, this is a 6, and this is a 4. Okay, 6 over 4, that is 3 over 2. When n is 4, this is 8. 4, this is 5. This is 8 over 5. So as n goes to infinity, again, you see that this sequence also go infinitely. Okay, but the question will now be that the question later will be that this type of sequence is either to converge or diverge. Okay, converge means it has a limit, and diverge means it has no limit. Okay, but at the beginning of this course, I want us to take something into notice. Okay, you'll see that the first sequence here starts from a number. Okay, that is 1 is more than 1 over 2. 1 over 2 is more than 1 over 3. 1 over 3 is more than 1 over 4, and this is going to 0. Okay? Similarly, the next example we are considering here is that we see that the first member is 1. The first member is less than the succeeding term, which is 4 over 3. 4 over 3 is 1.33333. And 1.333 is 3 over 2. 3 over 2 is 1.5. Okay, and this also will. Okay, so we will observe that all this time, okay, till we get to the last number, okay, is a member of R. Okay, is a member of R. Okay, so and therefore this is a sequence. Is a sequence of numbers. So that is a second example. So let's look at another example. Where I'm doing is, observe that this is decreasing, and this sequence here is increasing. Okay. If you want to know the last number, okay, just take the limit of this sequence as n goes to infinity. Okay. If you take the limit, the last number here, okay, is going to be 2. Okay. But sequence literally means a number that goes without bound. Okay. That is good. Number goes to infinity. Eventually, okay, if such a sequence meets some certain conditions, okay, then it will have a limit. Okay. Limit means it will stop somewhere. Okay. Whereas at that point where it is stopping, there will be a lot of cluster point around it. Okay. The cluster, okay. For example, if this is 2, okay, there will be a lot of points, okay, that look like 2 as n goes to infinity. Okay, those points are called the cluster points. Okay, if you can magnify the points, you see that around 2 there are billions of numbers, okay, that look exactly like 2, billions of numbers. Okay, so let us look at other examples. So example 3, we can also have a sequence of this form. C that was meant here is a constant. Okay, a constant could be any number. Okay, you can say 2, but I'm using a general concept here, or a general notion. You see that since this C is independent of n, okay, so it means when n is 1, we have C. When n is 2, we have C. When n is 3, it is C. This goes, okay, infinitely. Okay, so it's a constant, okay, and it goes. Okay, so if you want us to write the last number, the last number is going to be C also, because since it is a constant, this will not change. Okay, I'm just giving us this, okay, but later some condition as the sequence there will, okay, there are some conditions that must hold before we can say the sequence is convergent. Okay, I'm just trying to show us, okay, that if there are some sequence that goes, okay, and if they go, they may eventually stop somewhere. If they meet some certain conditions, and if they do not meet such conditions, they go. Okay, but the first 3 examples I've given you so far, okay, meet those criteria of convergence, and that is why we are able to determine their last number. Okay, so the term this is also a sequence of real number. Okay, for example, if you pick a number 2, and 2 is repeated every year, okay, 2 is a real number, okay, because you can find 2 in if I say -5, and this is a -5, -5, -5, -5. -5 is a real number, okay, and because of that, we call it a sequence of real number. Okay, now let us proceed to look at other examples. So, number 4. Again, this time, when n is 1, the first time will be 2. And when n is 2, this should be 4 plus 1, that is 5. When n is 3, this should be 9 plus 1, that is 10. Okay? When n is 4, this should be 4, that is 16 plus 1, that will be 17. And this goes, okay? Now, if you are looking at this number, okay, you see it is going up, that is, it is increasing. This type of number will eventually diverge. It will have more n, okay? And but where we are going is the result we are getting can be found, okay, in the set of real numbers. And because of that, this is the sequence of real numbers. Okay, so let us pick some examples under some notion that we have already known. That is the notion of a arithmetic progression or geometric progression. Okay, you will definition of arithmetic progression. Okay, when we have a sequence of number, okay, and we are able to know the first member of that sequence, okay, and that sequence has constant difference, okay. Such a sequence is also a sequence of real numbers, okay. So I'm just writing the name just to, since we know what is it before. Arithmetic progression. Okay, I'm about to give a sequence which has a constant difference. Okay, and follow the law we have said there. Okay, so the sequence. Okay, we can write the general form and can as well write the. Okay, let us write 2n minus 1. Let's start from 1 to infinity. Okay, this is a sequence of odd numbers, and we'll see later that this number, when n is 1, it should be 1, when n is 2, this should be 3, this should be 5, this should be 7. You see that the difference here is 2. The first successive terms, the difference is 2. The next 2 successive terms, the difference is 2. The difference is 2. Okay, and this goes, okay, up to infinity. Okay, so it's also a sequence of real numbers. And this is the general term. Okay. So under this, you can generate different type of sequence of real number. Okay. For example, if you want to use the general term for for generating sequence under this, okay, we can say XL, as we know in the formula, A is the first term of the sequence, and then D is the constant difference of this. Okay, so you will see here that if you know of any sequence, okay, or you want to find any sequence here, just give the first member. So since we know the first member here, the 1, okay, we'll give this 1, okay, Okay, and the constant difference is 2. Okay, that is constant difference is 2. The first member is 1. Okay, you will see that this is exactly this. Okay, so this is 2n. When you open the bracket 2n, you get what we have here exactly. Okay, so to generate different type of sequence that follow from the arithmetic progression, one can obtain them using this formula. Okay, but what we are saying here is that this sequence is the sequence of real number. Okay, now 6. Okay, next example. We also have geometric progression. So, unlike this arithmetic progression, these are sequence with constant ratio. Okay, and we can obtain them differently. When we see constant ratio, there are of 2 types. Okay, we have the case where let's have the general case here. So any sequence or anytime xn equal to a r n minus 1. Okay, where n starts from 1 to infinity. N starts from 1 to infinity is a sequence, okay, where A is the first term and R is a common ratio. Is a common ratio or constant ratio. Okay? So it's a sequence of real numbers. Okay? So anytime that we can obtain from this is a sequence of real numbers. So for example, we may now ask that if R is 1/2, okay, and the first term is 1, okay, we obtain a sequence so e.g. if a equal to 1 and r equal to 1/2, then we have that xn, where n starts from 1 to infinity, will be equal to this. Okay, 1/2, which will be 1/2 raised to the power of a minus 1. Okay, I think if you substitute this into the formula, this is what we have. And then let's see some of the elements we can obtain from this. So when n is 1 minus 1, that's 0. Okay, 2 raised 0, that's 1. So 1/1 is 1. Okay, that's what should have the first time is 1. Okay, so when n is 2, it's 1/2. As you can see, if you take the ratio of this, that was 1/2. The next time you go to 1/4. The next time is 1/8, and this goes like that. Okay, so this is one example under the arithmetic progression. Okay, and then we can choose R to be more than 1. Okay, because there are difference between when R is less than 1 and R is greater than 1 under the arithmetic progression, under the geometric progression. Okay, the difference is that if the common ratio is less than 1, okay, that sequence is going to have a limit. Okay, that is can times n to infinity and has the last number for the sequence. On the other hand, if R is more than 1, okay, so such a geometric progression will tends to infinity. Okay, it tends to infinity. That's the major difference in them. Okay, so now let's take the 7th example. I'm giving you some of these examples so that we know that when we are talking about sequence, okay, we are talking about sequence generally, either in mathematics or they use in other areas of science or engineering. Okay, in optimization, in economics, in social sciences, okay, such as in accounting. Okay, you can formulate a sequence from there. Okay, also under the when we are writing the programming, okay, and we are using the for loop, okay, we are using the for loop in the programming, okay. So if you are nesting a particular loop, okay, that's the sequence, okay. So we can formulate sequence in several ways, okay. But let's see the one we have. The one we are about to talk about is the Fibonacci sequence, okay, and I think we talk about this sometime in one of our class. So Fibonacci sequence, okay. So this sequence is a simulation sequence, okay, and I think I've told you something about this before. This says if the first member is 1, that is, if the first member, if x1, that is, x1 here is 1, and x2 is also 1. So then the term xn equal to xn minus 1 plus xn minus 2, or xn minus 2, xn minus 1. Okay, any sequence that we can formulate from here, okay, it's called the Fibonacci sequence. I want to know whether that is clear. Any sequence you can formulate from this arithmetic, okay, it's called a Fibonacci sequence. Now let's see when n is 1 here, what do we get? So let's see some of the items in the sequence. So the sequence now is according to the information we have here, the first time is 1, the second time is also 1. Okay. Now, okay, sorry, it should be 3. Okay, because when n is 3, we have the x3. Okay, you can change this is 3. So when n is 3, okay, here we have x3. Okay, and in the inner something here, when n is 3, we have x1 plus x2. Okay, that means the next time here, which is x3, is going to be the addition of two preceding successive terms. Okay, and that will be 2. So when x 4, x4 is going to be this plus this. Okay, that's what the formula is saying. And this should be 3. When x is 5, this will be 2 plus 3, that is 5. Okay, the next one will be this. The next one will be this. The next one is going to be this. Okay, the next one is going to be this. Okay, so this is a 34. Okay, and so on and so forth. Okay, so as you can see, this sequence is also a sequence of numbers. For these are the items that we have in it. Okay, so yes, and that's what we refer to as Fibonacci sequence. So it is a simulation function because we get the information from the preceding informations. Okay, and this is where the idea of a simulation starts from the Fibonacci sequence. Okay, and then it has upgraded up to what we have in technology today. Okay, and it is what we study today in the machine learning or other areas of artificial intelligence. Okay, this is where it starts from. Okay, simulating, that is getting an information based on the preceding informations. Okay. Okay, so from this Fibonacci sequence, we can obtain another form. Okay, and this form is called Fibonacci ratio. Fibonacci ratio. Okay, and we can only get this by taking the ratio of two successive terms here. Okay, that is, I will take the first two numbers here and take the ratio of this, take the ratio of this, take the ratio of this. Okay, and do that again till infinity. Okay, so we'll do that. Okay, so this is the term xn equals to this. Okay, this is to take the ratio of these two, it's going to be 1. The next, to take the ratio, it's going to be 1 by 2. The next one, take the ratio, that is 2 by 3. The next one, if we take the ratio, that will be 3 by 5. Take the ratio of the next one, 5 by 8. Okay, and this also goes, okay, so infinity. So this term is also a sequence of real numbers. Okay, so but one thing we observe here is that Win Joby Samuel says I should retake the Fibonacci sequence, especially the formula part. Okay, this is the formula part. Okay, what we have done is the way we have designed the formula is to add the first two successive terms together. When we add this together, we have 2. Okay, so now since we have 2, that 2 is going to be the third term. Okay, so since I've got the third term, I will neglect the first term. Now to have the next two successive terms. I will ignore this, then I take this. So I will add this again to get the fourth member. Okay, then I will ignore this again. Add this up again to get the next member. So I will ignore this, add this again to get this. Okay, so this is how the formula is designed here. Okay, and it is a simulation sequence, as I said earlier. I don't know if I have answered that question. Okay, so And here is a Fibonacci ratio. I want to tell you something about this. Okay, if you look at, if you have to write out this in the decimal form, you see that this type of sequence is oscillatory. Okay, from the beginning, but at the end it converges. Okay, so the first number here is 1. The second one is 0.5. Okay, again, this is 0.6666. Okay, this is 0.6. Okay, it is like a time. It goes up. It's already at 1. Okay, let's say this is the graph. It is 1 here. This is half. Then from 1, it comes to half. From half, it goes up again, come down again. Again, the next one should come this way. So forming a zigzag from the beginning. Okay, so later it will be this form. Okay, so that is Fibonacci sequence. And as it is going, it's going to stop at a particular number called the Fibonacci, the golden ratio. Okay, I think I've said this earlier before also. The last member of the Fibonacci ratio is referred to as golden ratio. Okay, and the value, okay, is 1.6, something like that. 1.6, right? Okay. So that's the Fibonacci ratio. So let's have one more example, then move on to other things. So that is what we refer to as compound interest in the area of accounting. Okay, and from the formula of the compound interest, where we have the compound interest to be the principal multiplied by some terms there. Okay, so we can formulate a particular sequence. Okay, that we refer to as I will just write the sequence here. Okay, but we can find out what is the formula for compound interest. Okay, so we have a kind of a sequence. Of course, the sequence starting from 1 to infinity. Okay, this type of sequence 1 plus 1 over. Okay. Yes, it's like the other compound interest. This one is like a principal. It's like you are investing a particular amount into a business, and you tend to get your interest. Okay, if any is running here, it means you have the interest has been compounded by one time. If n is 2, it has been compounded 2 times. If n is 3, it has compounded 3 times. If n is 4, so the more the compounding, the more the interest. Okay, so here is just to see the behavior of the single sequence. Okay, that we have taken from the compound interest. Okay, so here, if n is 1, okay, so the first member of the sequence is 2. Okay, so that is wherever we see n, put 1. This is 1, 1, 1, this is 1. Okay, so it means if you are investing into a particular business, okay, and then this is money you are putting into something, and then maybe for let's say, because you have compounded 1 time, let's say that represents 1 year. Okay, so it means after 1 year, your capital has been doubled, okay, and it is 2, okay. So what if you wait for 2 years and say, oh, I'm not using this now, let me wait after 2 years? Okay, so let's okay, so let's see what let's see what this will give us after 2 years. Okay, so we combine the second time. Okay, so we'll see that here. So when n is 2, this is 1/2, this is power of 2. Okay, so this plus this 1/2, that will be 3/2. Okay, square. Okay, you can use your calculator to get 9/4. Okay, 9/4. Let us write it that way, and then we can 9/4 is 2. 9/4. If you do it that way, and we can also write it as decimal. Okay, whichever way we choose. Okay, so when n is 3, this will be 1/3. This will be 3. So 1 plus 1/3, that will be 4/3 raised to the power of 3. Again, if you take the cube of this, you can write it in decimal. Okay, so this is how this continues. Of course, this is going to be 2.2. This is going to be 2.5. Okay, then if you find this, okay, you also have to point a number. Okay, but if you continue to compound, okay, up to infinity, okay, the sequence has a least member, okay, it is referred to as the exponential. What we are saying is that as n goes to infinity, the last number of the sequence will be exponential, and where exponential will be this. You will recall we have said exponential number is an irrational number, okay, but the first 3 members are 2.718. Okay, it means as this is going, it's going to stop it. Okay, that means if you are compounding the interest, okay, at a particular rate given here, okay, so the interest can be more than 2.71 and a lot of decimals here. Okay, so this formula is very, or this sequence is very useful in that area of the accountant. Okay, and they are using this in many of these organizations to calculate the interest. Okay, so yes, let me know if there is any question in the comment section, because I'm leaving this part now. Any question? Okay, no question. All right. So what we are going to look at now is we have seen a lot of type of sequence. Okay, none of this sequence, when we say a sequence is bounded, okay, you will see that some sequence goes without bound and some, okay, has a bound. So when we say a sequence is bounded, okay, so we want to give a general notion for that, and then we'll give ourselves some examples. We can pick from the one we have listed there. Okay, and we can give other ones as well. Okay, so when we say sequence is bounded, so there is a general law. Okay, but taking the law one after the other. Okay, from what we have known earlier. So we'll refer to this as the definition 2.2. Okay. What we're about to talk about is bounded series. Okay. So before we talk about the bounded sequence, okay, we'll talk about two notions. Okay. When we say bounded, it means something that is bounded above. It has beginning and it has an end. Okay. Or it has a beginning and it has an end. Okay. That is bounded. Okay. But to make it more understandable, we first consider a sequence that is bounded below. Okay, that is a sequence that has a beginning and a sequence that always has an end. It doesn't have a beginning, but it has an end. Okay, so when we now bring both of them together, okay, both of them now constitute this definition. Okay, so let's take them one after the other. Okay, so I will label this now one. A sequence xn. Okay. So when we say sequence xn, it means we are referring to any sequence from what we have discussed earlier, or from any sequence we have not even talked about here. Okay. Hello, I'm just joining the live. Can someone summarize or explain it? Okay, well, nobody will summarize this for you here. Okay, you have to wait till the end of the class and go through the video again. We don't understand, go through them again. So after you have watched several, okay, and you are able to get it, you can then put your question forward. Okay, so the sequence xn, like I'm saying, when we say sequence xn, it means any sequence at all. Okay, whatever sequence one can ever think of, the sequence we are referring to here. Okay, so the sequence xn is to be bounded below by a real number n if xn is less than or is greater than or equal to n for each n in n. Okay, so we'll say a sequence is bounded below if we can find a real number n. Okay, let me use the difference this to write this. Okay. So mine is so the sequence is bounded below by a real number n if xn is greater than or equal to n for each n in n. Right. So for each n in n. So now let us see some of the examples of a sequence that has been bounded below. Okay, we can pick from the example we just finished now. Okay, so let's see the example. Consider okay. So like I said, the small n means minimum. The way it is used, the small n means minimum. Later, we'll be using capital M to represent a sequence that is bounded above by capital M. Okay, you will recall in our previous physical classes, we have described small m as the minimum of a particular set. Okay, and the capital M, okay, the same notion is taken to consideration here. Okay, so if I say m here means the minimum of a particular set. Okay, so consider the Fibonacci sequence. The Fibonacci sequence. So this is one of the sequences we consider here, where xn is equal to 1, 1, 2, 3, 5, 8, 13, and so on and so forth. So you will observe that this sequence, okay, is going to infinity. Okay, so like I said, let n equal to the minimum here of xn. This is xn. Let n equal to the minimum of this. So if you look at all this, okay, like I said, the sequence is going to infinity. What is the minimum number here? I want the audience to tell me what is the minimum number in that sequence. What is the minimum? Samuel. What is the minimum of that? Okay, 1 is the minimum. Thank you. So 1 is the minimum. Okay. Again, who can tell us what is the maximum? What is the maximum here? Yes, Abulaji. Yes, 1. I got that. What is the maximum? You can write it in ways. If you can write it in numbers. No, the maximum can be 13. I put dot here. This continues. Dot means it continues. The maximum can be 13. I'll stop. I can generate one here to be 8 plus this to get the next number. Okay, it doesn't mean we are stopping at 13. The next number here is 21. Okay, the next one after that is 34. Okay, but I've given you a kind of a hint. Okay, somebody says infinity. No, yes, it goes to infinity, but this time, since infinity is not part of the real number, we have said this in the class. Since infinity is not part of the set of real numbers, okay, we say the maximum here is empty. It is because infinity is not part of real numbers, but we know it goes down to infinity. But infinity itself is not part, okay, of the number, so it's not 0, it is empty. We have said this in the class. In one of our last class, we have said that. So, and because of that, this sequence only has a minimum, but no maximum. Therefore, the Fibonacci sequence is bounded below. Is bounded below. Zubair and if I've attended to that question, okay, please correct yourself. The maximum is empty, it is not infinity. If I say the supremum is infinity, no doubt. But if you are referring to the maximum, infinity is not part of the elements of real numbers. Okay? And because of that, it is empty. We have said that in our last research classes. Okay, so therefore, So let us let us make a confusion that will be understanding. Since the sequence, since xn is greater than or equal to n, which is 1. Okay? So if you take for each n, for each n you pick, this sequence here, if I pick any number here is more than 1. N is 1, 1 is equal to 1, when n is 2, 2 is more than 1. Okay, that's why we are using greater than or equal to. 3 is greater than 1, 5 is greater than 1, 8 is greater than 1. Okay, so for each n I pick, okay, we have a member that is more than 1. Okay, what it means is that that sequence is valid below. Okay, so then it is bounded below by 1. Okay, so that's an example of a sequence that is bounded below by 1. Okay, so that is the first definition we are looking at here. The second definition will be a sequence that is bounded above. Okay, a bounded above sequence. Okay, I assume this is taken. Okay, so what is it say? So 2, a sequence xn is said to be bounded above by a real number if xn is less or equal to n for each n in n. Again, we are minding this n. This n here will be the capital N. Okay, so let's see also, for example, we want to see an example of a sequence that only has maximum but no minimum. Okay, so here I want to consider the sequence so the sequence, or let's say consider the sequence xn equal to okay, the sequence xn equal to n Okay, so this sequence, when we take the first member here, it will be -1/2. Okay, the next one will be -1/2. The next one will be -3/2. The next one will be -2. The next one will be -5/2. Okay, the next one will be -3, and this is going like that. Okay, so what you are seeing here is that if you are to rearrange this sequence on the number line, okay, let's see how this behaves on the number line. Okay, because most part here is negative, let's say this is 0. Okay, this is -1, -2, -3, -4, and this goes thus. Okay, and you will see that we also have -half. Okay, so if you look at this set, okay, I want to take the minimum, n, which is the minimum of this sequence. You know, the minimum will be the very smallest number, okay, and goes us to the largest negative infinity. Okay, since we know the minimum is supposed to be negative infinity, but since negative infinity is not part of the set of real numbers, okay, we'll say the minimum here is empty. So it means this sequence has no minimum. Okay, however, it has the maximum. Okay, let m represent the maximum of the sequence. And if you take the maximum here, okay, it is half. Okay, if you look at here is the maximum, because this is decreasing. Okay, okay, it's the maximum. Okay, so this is negative half. Okay, so do you have any question on this? Yes, okay, WinJobbies has already said that the minimum is empty, while maximum is -half. Yes, that's correct. Okay, so and because of that, this sequence is bounded above by -1/2. Okay, you can conclude using that now. Okay, you can conclude. Therefore, this sequence is bounded above but not below. Now, this will now lead us to the next definition. I assume you have taken care of this. Now, the sequence xn is said to be bounded. Now, we will remove the word below and above. The sequence xn is said to be bounded. Okay? If there exists real numbers m and okay, such that the small m is less or equal to xn and this is less or equal to capital. Okay, if this happens for each n in n. Okay, let me read this comment. Yes, we can see that Samuel. Samuel is really following. Yes, that is the conclusion here. You have got that right. Now we are not talking about this sequence. Okay? The sequence let's say we said will be bounded. We have removed the word above and below here. Nothing like that. Okay, but when we say bounded, okay, it means such a sequence has a minimum, such a sequence also has a maximum. Okay, let's see, for example, the sequence xn equal to, I want to pick this from the one we have earlier, 2n over m. Okay, let us list some of the items here. Okay, the first member is 1, when it is 1. And the next member is 4 over 3. The next member is 6 over, that is 3 over 2. 8 over 5. And then this goes, okay, if you are able to get the limit of this, okay, if you find, as n goes to infinity, if you find the limit of this, okay, you have said that this is 2. Okay, clearly, n, which is the minimum here, is 1. Clearly, the minimum is 1. And the capital M, which is the maximum, is 2. Okay? Since the sequence in question has both the minimum and the maximum, okay, then we conclude that the sequence, okay, that this xn is in between the range of 1 and 2. Okay? So okay. So therefore, it is a bounded sequence. Okay? All right. Okay, I think that is taken now. So now we can have any other example using the previous examples of sequence that we have considered. Okay. So next is want to give a kind of a formal definition of bounded sequence. Okay. This also is bounded sequence. Okay. But I want to give you another formal one, but I will label this form. Okay. So all these, put them in your wallet. Enter, I want to identify sequences that are either bounded or not bounded. These are something we use. Okay. So it is worthy to note that if a sequence is only bounded below, that sequence is not a bounded sequence. If a sequence is only bounded above, that sequence is not a bounded sequence. I repeat, if a sequence is only bounded below, such a sequence is not bounded. Okay? If it is bounded above, it is not bounded. Okay, we'll say it is bounded if it has both the smaller part and the upper part. Okay, as it is seen here. Okay, so the next thing we want to give is just to give a formal definition for boundedness, which also holds for this, and then also another bounded sequence. So I will leave it as 4. Okay. So a sequence xn is called a bounded sequence. So there exists a positive number n, if n is positive, such that the absolute value of xn is less or equal to n for each n in n. Yes. So now we say sequence is bounded if we can have a positive number n. Here, n also means the maximum of that sequence. Okay, but here, when we take the absolute value of that sequence, the absolute value is also less or equal to this. If that happens, okay, this one is going to be bounded sequence. Okay, a sequence that will satisfy this condition also definitely has a minimum. Okay, so note. So by definition of absolute value, as we have said in our last virtual class, by definition of absolute value, we can interpret this. Okay, we can interpret this to be. We can interpret this also means this minus n less or equal to xn less or equal to n. Okay, so that's by the definition of absolute. So that is that. So the previous example that we have considered to be bounded also satisfies these conditions. Okay, and many other ones that one can have. Okay, so this is all about the bounded sequence for now. Okay, so let us now discuss another concept under the sequence of real numbers, and this is the notion of convergent. Well, before we move to that, I don't know if anyone has any question to ask. Any question? Popola, if you are there, you have any question? Any other large day? So there's no question. Let us continue. Okay, yes, sir. We ending the class by 2 p.m. Yes, the class is by 2 p.m. What's the time now? What is the time? Oh, yes, we are ending the class by 2 p.m. Okay, and it's almost 2. So if you have any questions, so let's we can stop here. But we also have Akulade Afix. This is the first time you will be commenting. Do you have any question? So I'm with you. Any question? So when next we meet, whether physically or virtually, we're talking about um, convergent sequence, okay? And we'll try to relate convergent with bounded sequence, convergent sequence and bounded sequence. What is the relationship between them? Okay, and what are the reservation or drawbacks from the part of the bounded sequence? We'll try to address that in our next class. Okay, so if there is no question, I just want to say something here. Okay, no question, no question. So if there is none, so I think you can draw the curtain here. Okay, so bye for now.